Cyr-Racine here. He's from University of Columbia, working with Cyr-Racine. And he did his undergrad in McGill, working there with Robert Brandner. And yeah, today he will tell us about atomic parameter.
Thank you. Thanks for having me. It's a pleasure to be here and be talking about this work I've been doing for quite a long time right now in collaboration with my PhD advisor, Cyr-Racine. I'll start this talk with some general thoughts about dark matter, because I realize that not everybody is thinking about dark matter every day, as much as I do. And I want to briefly discuss the idea of inferring the invisible. Cosmologists today are faced with the fact that most of the content of the universe is things that we cannot see. And so we need, as a scientist, we need to infer the invisible. But the idea of, having an element that you cannot see, it dates back all the way to ancient Greece with the work of Plato. So Plato was a very smart guy, and by talking to his friend who was a mathematician, he knew that there were only 5 regular 3-dimensional solids, and Plato was convinced that the world was full of symmetry and harmony, and the thing is, that he knew of only 4 primordial elements at a time of fire, water, earth, and air. And since he believed all these symmetries, he said, well, there's 5 solids, there's only 4 of them, and there must be something else, something invisible, which he called the quinta essentia, basically the 5th essence. And sure enough, fast track more than 2,000 years, and here we are as cosmologists, and basically face the same fact that we have some observation that tells us that there's something out there that we cannot see. We need to infer the invisible.
What are the 5 regular 3D solids?
All right.
So, I wonder, what is a regular 3D solid?
It's pretty much all the faces are the same.
Okay.
Like a cube is the.
So there's tetrahedron sort of.
Yeah, there's like 10. I think the biggest one has 20 sides. Right.
Tetrahedron cube, octahedron.
Yeah. So you can. Yeah.
Nice.
So talking about dark matter, since this talk is mostly about dark matter, the first hint that the universe we live in was populated with something invisible to us, human, was from Zwicky, which in the early 1930s, by looking at the coma cluster, the dynamic of all the galaxy moving in the coma cluster, inferred that most of the matter in that object was actually non-luminous and dark. And that was the first evidence that there's something called dark matter in the universe. The sad thing is that for almost 40 years, his idea was mostly ignored by the scientific community and considered as some kind of exotic observation that might be resolved might be resolved in the future while we get better observations. And the scientific community failed to realize that Zwicky had really made a groundbreaking discovery. So it took about 40 years, and in the late 70s, with the observation of the galactic rotation curve, suddenly dark matter was the big thing, and really was propulsed to the mainstream of science, and becomes a pillar of modern cosmology. And today we are, 30 decades later, and we still talk about dark matter because we don't know what it is, because we don't have a better name for it, because dark matter really parameterizes our own ignorance of what this thing is. And it's not about like a trying. There's been a tremendous amount of scientific effort going into trying to identify what dark matter is, and yet we still don't know. It's almost a bit embarrassing for cosmologists. But that doesn't stop the mainstream world to completely dissolve the idea of dark matter. And dark matter nowadays, supplements, beer, distortion, music, books, whatever. Dark matter is everywhere today. And as scientists, though, we're still struggling with what it is. We do know something about it. We know it comprises about 83% of the matter content in the universe today. And in the early universe, at the time of decoupling, was even more important than it is today. everything we know about dark matter, we observe it through its gravitational signature. Now that might be a bit worrying, because if you look at Einstein's equation, there's two sides to it. So dark matter explanation says that there's some forms of matter that contribute to this energy momentum tensor that give rise to a gravitational signature that we observe through normal matter, baryon matter, etc. There's other explanation that says, oh, maybe it's not, TMU is just baryons, but there's something else in the gravity sector that makes us think there is such thing as dark matter. And the issue is still not settled, although this side has many more problems than this side, and today, of course, we're going to focus on the dark matter explanation of this puzzle. Three of the things we know about dark matter: it's cold, so it has negligible free streaming, doesn't move much in the universe, so we don't want this. It's collisionless, so it doesn't transfer heat over a large distance, doesn't thermalize, so we don't want this. And it's non-interacting, it's neutral in the standard model, so it doesn't re-interact with baryons and photons. So and these three conditions form what we call the cold dark matter paradigm, which has been extremely successful at explaining various cosmological and astrophysical observations, starting with the cluster dynamic that Zwicky observed a long time ago, and the galaxy rotation curve. More recently, the CMB has been leading to some very tight measurements on the presence of dark matter, observation of galaxy distribution in the universe. It's totally consistent with the existence of cold dark matter, and observation of exotic objects, just like the Willock cluster, reinforce the fact that dark matter is really doesn't have much self-interaction. So we have this successful paradigm. But of course, if that was the end of the story, we'll be happy out of a job and we can go home and read a book. But of course, this is not the end of the story. There are hints that there might be physics beyond cold dark matter. And so I'm going to talk about just two hints here. There are many more. And of course, these are just hints. They're not, definite observation that is proof that cold dark matter is just wrong. But it's just, little observation that makes you think about, what lies beyond. Two of these observations I mentioned today have to do with dwarf galaxies orbiting in our own Milky Way, or actually other galaxies too. So the first hint is this mass profile of these dwarf galaxies called dwarf spherical. So these galaxies have some mass profile called the dark matter is distributed inside, and you can go and measure these things. Of course, these observations are very hard, but you can go and measure how the dynamics of how a star rotates and moves in these dwarf spherical. And from this observation, you can infer how dark matter is distributed inside. And then you can go and use a cold dark matter and make an n-body simulation to compare with your observation. And the thing is, once you do a cold dark matter simulation, you obtain that the dark matter inside these dwarf turtles should be quite cuspy as a density profile. While the observation suggests that it might just be a core. So cold dark matter said, oh, we should have a cusp, so the slope, the mass function should be around here, and then you go and observe, and it's significantly different from what you expect on cold dark matter. Of course, this n-body simulation don't contain baryons, so there's other issues you might think of. That might explain this, but it might also indicate that the dark matter is less simple than just cold dark matter. Another observation from dwarf galaxies has been pointed out quite recently by Boyle and Colchin, very recently, is that so in n-body simulation, if you simulate like a galaxy Milky Way-like dark matter halo, and you look at the sub-halo inside that halo, you realize that the most massive halos are way too dense to host a bright dwarf spherical that we observe today around our own galaxies. So basically, if you plot, this is where I'm missing the bottom. This is the velocity versus radius of these dwarf galaxies, and so these bands contains the sub-halos you get from simulation. And you have this large band here, which corresponds to the most massive sub-halos. And we don't observe any of these most massive dwarf spheroidal around the Milky Way in that band. So these are very massive halos which should have attracted baryon into them because they're so massive, and yet we don't observe them. So that's a problem with the end of CDM. And this is harder to explain than this because you cannot say, oh, it's a detection bias, we haven't seen these things, they're too faint. No, these objects should be very bright because these should be the most massive and have the most baryon. So this is hard to explain.
On average, how many should the Milky Way have?
At least a few, my hand. The thing is, basically, there's only one of the one we observed, and only Draco is, mildly consistent with it, right? I mean, if you put in 2 sigma something.
Is it really just a matter of the view? Because if you're not going to look at the brighter objects, you must be able to look at the galaxies as well.
You mean like
the brighter dwarfs?
Around other galaxies?
Yes.
I'm not sure this analysis has been carried for other galaxies. I mean, this is a recent. This is like 2 months ago. But people have shown though is that this can be relaxed very much if you actually introduce interacting darkness. And I'm going to talk about this. And that that's one of the motivations for atomic dark matter, etc. Yes.
Do people trust CDM calculations enough for these types of statements?
I mean, you mean pure kind of CDM n-body simulation? Yeah. So in the second paper, these people try to say, okay, so what if we will include baryon in the simulation? If there's some wacky astrophysics that can give us this, and he concluded that no, it's very hard to invoke strange astrophysics to explain this kind of thing. Here you could invoke strange astrophysics. One of the strange astrophysics is just include baryon in simulation, and that might just move it. But here, this is much harder. The last slide of motivation is about the complexity of the standard model versus the dark sector. Now we know from the standard model that it has the laws of structure, it has lots of particle, quarks, lepton, all the force carrier, the gauge group structure, and etc. So there's a lot of richness in it. Well, usually when we talk about the dark sector, we say it's a dark matter. It's like one particle, like a WIMP, and that's it. That forms the dark matter part, dark matter side. Now, if you look at this, we compare these two. I mean, it seems to me that if there's so much structure here, why there shouldn't be a lot of structure in the dark sector too? So in the model we're going to talk today, it's an example, a kind of minimal example where you introduce new structure in the dark sector, and then you can ask the question, is it consistent with cosmology, etc. And how much freedom do current observation leave for new structure in the dark sector? And the answer to that is a fair amount. You can do quite a bit, and yet respect cosmology and astrophysics, etc. Now today we're gonna focus on this last model. So this is my personal list of favorite dark matter candidates, and I'm gonna focus on this last category here, inner sector bound state dark matter. So here's the outline of what we're gonna talk today. So I'm gonna briefly introduce this model called hidden charge dark matter, which forms the basis of what I'm gonna talk about, and talk about its constraint. Then introduce the actual model that I'm going to talk today, so atomic dark matter. I'm going to discuss its thermal history, its evolution of its ionization fractions, maybe decoupling, which is very important for structure formation. I'm going to discuss some constraints from cosmology, amount of power spectrum, cosmic part microwave background. And we conclude with some astrophysical constraints of the model, which turns out to be very important. And we'll mention some future directions for this particular model. Now I'm going to just briefly mention this hidden charge dark matter. So hidden charge dark matter was a model that was proposed a long time ago, but was kind of recycled recently by Jonathan Fang et al. And also by some other people like Caltech. And it's basically you have this dark matter particle which is charged under a hidden U1. So it's a U1 that doesn't interact at all with the standard model. It's just purely on the dark sector. And you ask the question, given the astrophysical observation we have today, is this model valuable? And these people went and done the constraint, and this is the mass axis. This is the equivalent of the fine structure constant. This is the U1, so there's a fine structure constant in this model. And you realize that given concerning the bullet clusters and the ellipticity of dark matter halos, because we observed this dark matter halos to be at triaxial shape, so they're not co-determinalized. So that is constrained on this kind of model. And we realize that only this corner of parameter space here is viable in these models. So these models are basically interacting dark matter because they're charged. As particles pass each other, you have some kind of Coulomb interaction, basically. And this kind of ruled out all this corner of parameter space because suddenly you start having interacting dark matter and you start making your dark matter halo very round. Now, what we're going to talk about today is actually atomic dark matter. And atomic dark matter lies in this corner of parameter space, where alpha is strong enough for these charged particles to actually bound together in a bound state. And the mass needs to be low enough that the number density is high enough that these particles can meet each other to actually form bound state. So in this upper corner of parameter space, you're going to form bound state, neutral bound states, which are going to change these constraints because now dark matter won't be charged anymore, but it will be a neutral bound state. So now our goal is we want to see how much we do this block change once you take into account that in this upper corner we actually form atoms. So here we go. Atomic dark matter. This model actually, if you go back to literature, was although introduced in 1986. And it was called shadow hydrogen at the time. It's been forgotten and then was resuscitated last year by David Kaplan. It's a simple model. You postulate a U1 gauge force, which is like a dark photons, and you have two fermions that have opposite charge. And for obvious reasons, we're going to call it dark electron and dark proton. These two things interact Coulomb-like interaction. There's as many electrons as protons, so it's neutral. There's no long-range force, no wacky cosmology is happening here. You only need 4 parameters to try to model the fine structure constant, the binding energy of this bound state using electrons and protons, the mass of the dark matter, and the temperature of the dark photons, which is usually parameterized by the C, which is the ratio of this dark sector to the standard model temperature, which is basically CME temperature today. And these parameters are subject to this constraint, which ensure the proton mass is real, not imaginary, because B is a derived quantity. As I was mentioning, this atomic dark matter has a rich thermal history, so we're going to spend some time talking about it, because this is really what we care about for cosmology. We really care about the different state of these dark atoms. So in the early universe, just like regular baryonic matter, everything is ionized, everything is strongly attracting, so we form really this hot plasma, and the dark fermions are tightly coupled to the dark radiation most perfectly. As time goes on and the dark sector cools down due to expansion in the universe, 2 important processes happen. First is recombination. Once the temperature of the dark sector falls below the binding energy, it becomes energetic works towards forming bound states in the dark sector. And the other process is kinetic and thermal decoupling between dark photons and dark electrons and protons. So when the interaction rate between dark matter and this dark radiation falls below the Hubble rate, this dark matter temperature decouples when the radiation pulls it radically. So we spend some time describing these two processes in detail. Of course, the nice thing about this is that this is very similar to normal hydrogen, so we have a lot of intuition about how everything works. So it makes our life quite a bit simpler, at least in some corner of parameter space. Now this is a model which is not completely free. We know you need to be to agree with cosmology, and in particular you don't want to mess up with Big Bang nucleosynthesis, which puts an upper bound on the number of relativistic species during this BDN. And the constraint is something like this, and once you work out the math, you find that the temperature of the dark sector should be about, at most, 3/4 of the standard model temperature. So it needs to be a bit colder than this CME. You have dark photons floating around today, they're going to be a bit colder than this CME, so that you don't produce too much helium in the early universe and so on. Now, just dive in briefly into recombination. Just like for regular hydrogen recombination, cannot happen by just directly recombining the ground state of the atom, because once you do that, you emit a very energetic photon that goes and just ionizes other atoms. That's very inefficient. So what you do is you consider case B recombination, which recombines to the second excited state, and then cascade down to the first excited state.
Sorry, I actually
Go ahead.
interrupted. This constraint on the temperature is not affecting your freeze out, obviously, right? I mean, the freeze out you're still saying it's just normal radiation, making the dark matter particles itself freeze out. You're not supposing any strong photon in the production of the dark matter itself.
No,
I'm just asking.
it's quite standard. So, so the number of charged particles in the plasma is governed by the Boltzmann equation for the ionization fraction, where I define this as the number of free electrons over the total number of protons as neutral dark matter particle. This is the normal equation you're going to solve for regular hydrogen. There's nothing new here. This prefactor encodes the fact that you recombine to n equal 2 states, and once you recombine to n equal 2 states, it can either be ionized again by a Laminar photon, basically, or you can recombine to the ground state by emitting a Laminar photons, or a suppressed two-photon process. And so that encodes the probability of all these different processes. And so everything else is described here. So this is very standard for this is just like regular hydrogen recombination. One thing that's a bit different though, so this recombination coefficient, which basically governs the rate of recombination. In previous studies of dark atom, people have used this kind of a canonical recombination rate, as you can find it in the Spitzer's textbook. So there's a few problems with this rate. First, it only depends on the dark matter temperature, so it misses the dependence on the radiation temperature. The thing is, there's two processes for recombining. There's spontaneous recombination and stimulated recombination. It's a quantum process with depends on photons. So this rate actually has a dark radiation dependence, although it's not there. So we'd like to include this. It also misses all the effects from the ion states, all the tail, the ion shells that are included into this. And the temperature dependence for very low temperature and very high temperature is not fully captured. So what we do, well, it's easy. We just go in and compute these rates from scratch. These rates are well tabulated. This is all atomic physics cross-section that's been worked out in the 1940s, 1950s. So you can go on and find it and then compute these terminal rates from scratch. And we use this method devised by Yassine and Yamoud, who's a postdoc at IIS now, where you actually include all the possible bound-bound transition. So we basically capture this ion state effects for free in the way. So we do that, compute these rates. So this is completely under control. And then you can ask, okay, once you do that, does it make any difference at all? In the case where you're in thermal equilibrium, which dark matter is basically the same temperature as photons, it doesn't make a whole lot of difference. This green line is rated by Spitzer, and this little difference here that is about 14%, and that's the if you're familiar with RECFAS, it's the 1.4 force factor you need to multiply your rates to get into account the ion states. Otherwise, this Picquignon et al., this is the rate that RECFAS uses. It's very good over most of the range where recombination happening. As I was saying, at early times and a bit of late times, the chemical rate kind of fails. Now, for usual hydrogen, this doesn't matter because everything is ionized all the way up here. But as we will see, this becomes important if Compton heating is inefficient at early times. So I think capturing this behavior right here is going to be important for later studies. Now, if the thermal decoupling happens before recombination, then the temperature difference between the radiation and the dark matter becomes important. And then their usual approach can fail. And then it becomes important to actually calculate these rates exactly. And this is what we do, so then we can capture all the spontaneous, the stimulated recombination accurately. And so all these rates basically under control. Now, once you go on and integrate your Boltzmann equation, in the strong coupling case, which is basically where the matter temperature just follows radiation temperature, it changed very little. I mean, this is basically 10% different in the end. And that's because most of the recombination process happens in equilibrium, where basically some approximation is completely valid and the actual value of the recombination rate doesn't matter. But in the weak coupling case, it can make a huge difference. I mean, this is like an order of magnitude in ionization fraction. I'm comparing, you see here the standard treatment or the improved treatment as described. And we see that for the weak coupling case, when alpha is quite small, you can actually have a difference. I mean, a lot of difference. I mean, you kind of miss the recombination redshift. The length ionization fraction is, an order of magnitude apart. So that computing these things accurately makes a huge difference. So recombination history is under control. Now, thermal decoupling. So when the temperature of the dark matter, the radiation start to decouple, so when you describe this transition accurately, in the early universe, you have all these collisions between dark photons and dark fermions, and basically the whole thing is thermal equilibrium at a single temperature. But once this thermalization rate falls below or becomes the same order of magnitude as the Hubble rate, then the dark matter starts cooling diabatically. And why do we care so much about this transition? Well, it's because, as I said, the recombination history is quite sensitive to the temperature of the radiation and the dark matter. And even more importantly is the kinetic decoupling, which kind of tells you what's the smallest dark matter tail we can form at any time, is also determined by this process. So we need to be able to capture this quite accurately. So in the early universe, for strong coupling, when alpha is big enough, the most important mechanism to exchange energy between radiation and the dark fermions is just Compton scattering. Just like for regular baryonic hydrogen. It's Compton heating is the most important mechanism, and that basically determines the temperature. So this is, the photons hit the dark electrons, give some energy, and so that's the process we care about. And for all interesting cases, Coulomb scattering between dark electron and dark fermions maintain them at the same temperature. Coulomb scattering is always extremely efficient. Now, the problem is that in the weak coupling case, when alpha is quite small or the dark structure is quite cold, Compton heating is inefficient. So now you start deviating from the regular baryonic hydrogen case, and you need to work a bit harder to think about, okay, what's really going on when Compton heating is inefficient at early times. Now, that means that you need to include some other mechanisms beyond Compton heating, and these are the bound-free processes described as photonization heating and photoreduction cooling. We also include free-free heating, free-free cooling, and I get this kind of scaling between these rates, and this is the Compton heating rate, which is t to the 4th, and then these are t squared to the 5.5. So they all have different temperature dependence, which means that for different values of the parameters, some of these rates become more important than others, and I will show a couple examples in a second. And at the end of the day, this is the equation you need to solve to get to actually solve the matter temperature. So this is the Compton heating term, which is going to be fine for regular hydrogen. This is ideabatic cooling from the expansion universe. And these are the new processes, these ones, that we now include in our analysis to better capture their energy transfer between the dark photon sector and the dark matter sector. Now, in such strong coupling case, I was saying, Compton heating is the most efficient. So here I'm plotting the different thermal rates as I mentioned in redshift. The black line is Compton heating. For the strong coupling case, we see Compton heating is just efficient compared to all the other rates. So, we just use Compton heating. If you're done, that determines your temperature.
So for small alpha d, basically there's a deterministic relation between VD and MD. So that's alpha squared MD. 1.5 alpha squared MD.
Yeah, so it's just a choice of parameter. I could have chosen the mass of the two fermions, but you can just invert it.
Well, I mean, assuming that one is much less massive than the other,
yeah.
then you.
That's right.
Then you just base well.
But within
factors of 2, it's just the lower mass fermion.
That's right.
So then within factors of 2, BB is basically alpha squared times n.
That's right. Yeah. Right.
So then you really have two parameters who vary alpha d and n.
That's right. Yeah, and all the constraints about the Venus show is going to be always alpha d against n.
Sorry. So is that value of BD already basically ruled out?
Which one? purpose of that. I'll show the real constraint in the end. I mean, I could have put this, you know, to like 500 keV or something. But the thing is, you just put everything to much larger redshift. So we're just taking this graph, pushing everything to 500 redshift. So just for numerical purposes, it's much easier to put it this way. So as mentioned in the weak coupling case, so in the weak coupling case, when alpha is quite low, then the green line, which is this photo recombination cooling, is dominating. So the Compton heating, the black line, is below, and you can basically forget about it. So that changed the thermal history quite a bit, because you know, if you would have considered only Compton heating, you would have obtained, so this is the red line here, that start diverging to the green line. The green line is the radiation temperature at a much earlier time than if you will take into account this photo recombination cooling and photo ionization heating. So basically, this boundary rate maintains thermal contact much longer than you would have thought by just using Compton. And then you know, it changes the temperature evolution quite a bit, and then back reacts in ionization fraction, as this is the same plot I showed you before for the weak coupling case. So it's important to include these extra ingredients to get a good idea what the late time ionization fraction is, because that's going to be, because this you're going to use that trope as a constraint at later times. Now, if we just put all the pieces together, say if you want to, one day you want to work in dark atom, you want to know if you need to work hard or no, you just use people, regular hydrogen recombination, but that's the number you want to compute. So the standard treatment of recombination, as described in Keebles and others, works as long as this epsilon, which is defined as this, is larger than 1. If this is smaller than 1, the standard treatment does not apply. And this is I'm plotting the log of alpha versus the log of the mass for different values of the ratio of the dark sector temperature to the center model temperature. And as is my guess, you know, it's always the low alpha, low mass region that you need to work harder, because this corresponds to denser dark matter, denser dark matter gas, and also a more weakly coupled, so that Compton heating is suppressed. So that's the number you want to compute, and as the colder is your dark sector, the more you need to work. It's just because Compton heating depends on T to the 4, and so it depends on C to the 4, and C is very small, you just suppress Compton heating by a lot. Okay, so now we have the thermal history under control, so we can solve for it and know what it is. Now we can start sometimes actual cosmology with this. And we want to solve all perturbation involved in this background that we just solved for. And so we have the dark matter evolution equation. Here I'm using the notation of Martin Birchinger, if you're familiar with this, but it's, you know, delta is basically the dark matter over density, theta is the divergence of velocity, and H is the potential in synchronous gauge, gravitational potential synchronous gauge. And so basically, if you look at these equations, if you're familiar in the case of the baryon, it's exactly the equation for baryon coupled to regular photons. And because now dark matter, since it's charged by U1, is be able to baryon. And I also wrote down the dark photon equation, which is the same thing as the regular photon equation. Now this term is an important term, because that term corresponds to momentum transfer between the photon sector and the dark matter sector. And if this coefficient here is large, then that forces these two things to be the same, which means that dark matter basically just carried along by these dark photons. It doesn't behave by itself, and the photons, if you solve their equation, it just oscillate. So we have this photon over density oscillation, and the dark matter is just dragged along. We'll show in a minute some plot of what that looks like in practice, but so when this coefficient becomes order 1, this is when kinetic decoupling happens. And kinetic decoupling happens when dark matter is able to move freely off the dark photon, so it doesn't interact much with the dark photon anymore. You have a question? Okay. So the moment when this happens, because as long as the dark matter and dark photon are coupled, structure cannot grow. It just can smooth out structure up to the scale that happens to rise in kinetic decoupling. And that determines the smallest dark matter halos that you're going to have at later time. So the time between decoupling is very important. And that's going to depend on the parameter of the model. Yes?
I mean, you showed that kinetically the recombination recombination radiation is important.
Yeah.
So in some sense, it should be important for the momentum as well.
Yeah, it is.
So are you including it then?
Yeah.
Okay.
Yeah, there are two terms.
Okay.
Actually, this is here. Here. All right. So there's a this opacity which is defines the inverse of this mean free path has two terms. This is the usual Compton term, which just corresponds to how much dark matter or dark photon can move before hitting a dark fermions, and then there's another term which is how much distant the dark photon can move before hitting an actual neutral atom.
And one thing, I mean, the recombination depends on the square process, so it's XE square.
That's right.
I'm kind of sort of surprised that XE square, especially the free tail,
yeah,
where there's already a percent or so that is still winning in terms of the parameters over the XE process.
I mean, this is which calculation you were showing? Talking about the XE law?
Yeah, where you show the cooling rates.
Oh, the cooling, yeah.
So the XE square process was still just because down to the
but as soon as recombination happens, it becomes very suppressed, and it drops extremely high.
But it was still rather high as well. Anyways, maybe not.
I don't know. I can show you again, but I thought here. Yeah, but as soon as recombination happens, it just rapidly drops.
Yeah, I mean, the Compton heating is XE, right? And the other one is XE squared. I mean,
yeah.
So
it does drop, but not as much, right? I mean, even in the other case, let us see the other case, right? So Compton heating drops, but the photo ionization heating drops quite as much, like XE squared. So you really see it. All right, so there's different regimes. So I want to talk about. So there's two terms in this opacity. There's different regime for all modes. Perturbation evolves with time. So when perturbation inside the horizon, nothing is happening. So we can forget about this. Now, as perturbation enters the horizon, this funky dark matter, dark radiation plasma, as long as the momentum transfer rate, which is given like this, where R is this ratio of photons to dark matter energy density, as long as this is much larger than the mode you're looking at, then it's a strong coupling regime, and you have undamped acoustic oscillation. You have this acoustic wave oscillating inside the horizon with not much damping. Now, as the frequency of the photons becomes higher than this momentum transfer rate, then you end up with an acoustic damping regime. Because these photons are oscillating very fast, but there's not enough momentum transfer to actually transfer this momentum to dark matter. So in dark matter, that experiences a drag, and that's damped perturbation on these guys. And finally, when this momentum transfer rate falls below the upper rate, there's no more coupling, and dark photons can free stream away, and dark matter can start, perturbation can start growing, just like regular cold dark matter. Now, that's the specific example of what I'm talking about. So strong coupling regime, again, the momentum transfer rate is much larger. It's larger than the double rate and the frequency of the photons. Now, they enter the horizon and start oscillating with the photons. The green line is the dark matter. The red is the dark radiation, which just follow each other until dark recombination, where the photons move away and dark matter can start growing, just like cold dark matter, but from a reduced amplitude. And that reduced amplitude is due to two things. During radiation domination, which is here, it doesn't experience logarithmic growth, so it misses on this. It also misses the horizon kick once the mode enters the horizon. So the difference between these two curves, between the cold dark matter curve and atomic dark matter curve, is only due to these two processes. There's no damping, acoustic damping going on. Now, for mode into the horizon before, a bit later, so again, enter the horizon, start oscillating with the photons for a long time. There's a bit of damping, it's much of time. And then when you enter this weak coupling regime, suddenly the dark matter cannot follow the photons anymore. it doesn't interact strongly enough with it. And then that kind of tends to damp the dark matter perturbation away. The photon just move their own thing, and then it can start growing again, pretty much much reducing amplitude. So the acoustic damping is suppressed power on the small scale. So you should have no structure at that time at these scales. And if you enter the horizon in the recoupling regime, again, if this momentum transfer rate is much smaller than the frequency of the photon, you just start oscillating, but the damping kills you right away, and you start again growing late after decoupling, but from a much reduced amplitude. So this is a different kind of scenario that happens now if you integrate this to lake time to compute the matter power spectrum today, so how matter is distributed in the universe. Of course, at large scale, it's BA is like cold dark matter. But again, this is DAO regime. So DAO is like BAO, this dark matter oscillation, because it's dark matter coupled to this plasma. You have this regime where you have on-damped oscillation. And then you have this damping tail here. And there's this important thing that this cutoff below which the power is reduced. And getting this cutoff right is important because it basically tells you what's the minimum mass of a dark matter halo you're going to get at the time. This is for the strong coupling case, so we have a long regime of undamped oscillation. In the weak coupling case, you only have few oscillation and they rapidly damp. Again, you get a cutoff, but the DIO regime is quite suppressed. So this is the kind of thing we're looking at. Again, and the thing, so if you look at the kind of data we have in the matter power spectrum, the linear matter power spectrum, and we have data from the Lyman alpha forest and so on, all the way to about here. So there's such a model with these parameters clearly ruled out. And it's clear you need to push this cutoff to much larger scale. Now, if you do that, it's not clear how you can be able to observe this because you push everything to small astrophysical scale where it's hard to see. So the cutoff scale is defined as the low density horizon akin to decoupling. And you can just make a simple spherical collapse argument how this cutoff momentum is related to the minimum halo mass, using this kind of spherical argument like this. And this, considering the dwarf galaxies exist, so you have a mass of 10 to the 6 solar mass and 7 solar mass, even at K cut should be at least 200 million parts. So that's kind of the lowest bound you can imagine having for these models. Again, this is very hard to observe, but it's not homeless, and actually involved into a mission to actually go and observe these things. So, and the way you want to do this, it's basically you want to observe this Darwin substructure using strong original landing. So the setup is, so just a little aside, it's going to take about 2 minutes here. So you have this galaxy that's lensing a background quasar, a high energy quasar, and it's lensing with multiple images. And so you see it today, it looks like this, like this. And then if you have precise measurements of these 4 images for the time delays, the position, and the magnification of this image, you can actually reconstruct the gravitational potential, the projected gravitational potential inside that lens, that galaxy here, and can infer properties about the dark matter substructure inside. And in particular, you're most sensitive to that cutoff in the mass function. So it's not hopeless that we will be able to measure actually that kind of mass cutoff that this kind of dark matter atomic diameter model predicts. And we have emission and flight system and everything planned. And you guys need to deal with that from Stucco, so I'm deeply involved in this.
Who is this being proposed to?
It was proposed for Explorer 2011. That's category 2, which is this short category 1. It's too bad. Next call is 2015, the next Explorer mission. The thing is, the analysis to actually extract from these kind of images properties of dark matter halo is still something that needs to be convincingly done, and that's actually something this is what I'm doing with that level.
So if one inputs a funky power spectrum to a CDM simulation, does one notice anything in the halo mass distribution?
that you extract is
Well,
such an observable?
I'm thinking just
Just
not
pure
about
embodied
the
simulation.
measurement using an indirect method like this, but just in a numerical simulation.
Okay.
I put it in above
Yeah.
the power spectrum, but I get anything noticeable in the mass.
Well, that's something
scale
that's,
mass.
to my knowledge, never been done. So I don't know. It's actually, that's part of the future work. Like how, if you have this DM regime, you have bumps in the power spectrum, how does the nonlinear physics basically takes this and modify it so obviously it looks at the same time. So I don't know, because if you just have the CDM, if you take into account nonlinear physics, you get this enhancement on a small scale. And it's likely that something like this is going to happen, but it's not clear if is it going to just average out these bumps, or is it going to amplify them? So it hasn't been done. To my knowledge, nobody actually attempted this. In the remaining few minutes, I'll talk about some constraint on atomic dark matter. First one I'm going to mention is, what can we tell with this observing cosmic microwave background? And this is more or less interesting because the largest effect in CMB of this model is just the fact that you have X-ray radiation. Having X-ray radiation tends to shift matter radiation quality. It does change the size of the sound horizon and so on. So it tends to shift all the peaks, acoustic peaks of CMB to the right, towards smaller scales. That's by far the largest effects that you can get in the CMB. Secondary effect you get is since dark matter in these models is interacting, so it contributes to pressure wave. Usually dark matter only contributes to basically the incoming wave. Usually it doesn't have pressure, so it doesn't contribute to the expansion wave. But in that case, it contributes to that. That changed the ratio of the odds and the peaks. So it kind of suppress the odd peaks compared to the peaks. But that's a very small signal. So there's not much CMB you can do with CMB, although as we're talking again this morning, spectral distortion might be something interesting to do at a later time. Another constraint, which is very serious, is from astrophysics, and I'm looking at dark matter halos and their shape. So now we have basically a model where dark matter is actually interacting. Because these atoms can bounce into each other, excite themselves, etc. And you have some residual ionization that can lead also to some interaction. So you need to be careful so that you don't start changing the shape of your dark matter halos, cluster scale, galactic scale, etc. And so you don't want to terminalize the halo. A terminal halo is basically a big round sphere, and you don't want to create that, but that's not what we observe. But we can in the X-ray image of these halos, etc. And that leads to a constraint. Basically, you want the terminalization time, which is just simply given by the number density inside these halos and some kind of collision cross section, to be less than the navigable time of these cluster or galaxy, etc. And if you use simple estimate of the geometric cross section for these atoms to bounce into each other, which is really like a very crude estimate, but it should give you the right order of magnitude. You get some constraint that looks like this. So it favors small alpha, ion mass, and ion binding energy. Now, for your own enjoyment, I've made some plots of what this looks like for different values of binding energy. So ranging from 10 eV to 1 MeV, 100 eV to 1 MeV. And basically, the allowed region that the bound I just showed you is this purple triangle here in all these plots. Now, as I was mentioning, there's only this other corner of crowded space where actually atomic dark matter exists. In this lower end, basically no atoms form because they're too weakly coupled, and the mass is too high, the number density is too low. These things never find each other. So it's clear that if the binding energy is 100 eV or less, so remember, atomic dark matter only lives above this red line here. Basically, there's no parameter space. Now, as you increase the binding energy, you're starting having some allowed region. Now, I should say, so this is everything below this blue line here is a constraint that I'll show you. This other purple line here is this consistency constraint to the binding energy I showed you at the beginning. Binding energy can be anything during the shows of alpha and m. So it needs to be just like the proton mass is not imaginary, etc. So this is the allowed region, and as you increase the binding energy, you open more and more parameter space. So it's clear that the binding energy needs to be quite large compared to Rickett hydrogen for these things to be viable astrophysically. And alpha needs to be quite large. It cannot be like very 10 to minus 6. It needs to be 10 to minus 2.
Well, if you think of alpha as 1 over logarithm, it can't be very small either. Is there a motivation for considering the motivation motivation for considering smaller alphas than 1 over logarithm?
I don't think. I mean, it's just that if you have very small alpha, to me, it's just that it's not an atomic dark matter. I mean, this is already my talk. It's not even my talk. So it's just really hidden charge dark matter, which already been discussed in other papers about work, and these constraints didn't work out. So what we really care about is this region, this upper region where actually atomic dark matter can exist. And that gives you the thing that, so these things are quite constrained. You don't have a lot of freedom. Astrophysics control these things quite carefully. So the key points, a few key points about atomic dark matter just to wrap up. So to me, atomic dark matter is a simple, effective test of physics beyond cold dark matter. And it's basically, as you see, as a minimal extension where you introduce some interaction in dark factor, but these are quite minimal. And it's simple enough that you can play around with it and make some clear prediction towards the model. And you can, you use it as a toy model to study more general dark sector with more interaction. It retains the success of cold dark matter on cosmological scale, so you don't mess up cosmology too much, but you just change physics on very small scale, inside dwarf galaxies or galactic scale and so on. But you leave the large scales alone, which is what you need. As I said, it has a rich thermal history. Kinetic decoupling is delayed compared to typical WIMPs, which means that power on small scale is suppressed compared to a typical WIMP. It makes easy decouplable predictions like the cutoff, these DAOs, and during the last one, it's not ruled out observations, although it's quite constrained. And so which kind of future direction you could go with this type of dark matter model? Well, so this dark matter model has internal structure, so you can excite it, some excited state in the dark photons, so you have a cooling mechanism. So that's concerning the model too. I haven't talked about this today, but we observe dark matter halos to be quite large. You shouldn't have cooled too much. That's really a constraint. Of course, the Webb cluster puts a constraint because this is interacting with dark matter. Another question I could ask is DO detectable, which is a point I made before about including nonlinear physics in the DO regime. A lot of people have worked into connecting this with standard models and direct detection signal. There's quite a few papers on that. All these dwarf galaxy physics concerning the problems I mentioned in the beginning. Can atomic dark matter solve these problems? Of course, there's alien U1 in a dark chemistry, can form molecular dark hydrogen, etc. So this is something you might need to consider. And it's related to these dwarf galaxies. How this atomic dark matter behaves when the first object collapses into dark matter halos. Something that's not being worked out. And so there's still a lot of exciting direction for this model, and I'll stop here. Thank you.
Maybe one urgent question to Jeff.
Why not dark reionization?
Sorry?
Why not dark reionization? Why not dark stars, dark?
Oh, dark star. People have worked on dark star, but it's. I don't think they worked on dark star in this model. But I think to form dark star, you need a lot of cooling, right? So you need to be able to cool your gas to form a very tightly bound object. And I'm not sure. That's going to violate other constraints in dark matter. You observe big galactic halos, galaxy clusters. So now you will need to come up with a mechanism that leaves the halo alone, and it's still gives you enough cooling to form dark stars. So it's unlikely that's going to happen, just because you need a lot of cooling. question.
Just under some basic points. So suppose alpha D is very big. Okay.
Yeah.
So then the dark matter recombines, all the universe is still relativistic.
You can push it all the way there.
So then, by the time matter starts to want to cluster, the temperature is way below the excitation, the ionization energy of the dark matter atoms, and so they're effectively billiard balls.
Yep. That's right.
But cross section can't be very big, or they would be strongly collisional, right? And so you have very strong limits in the cross section compared with an atomic cross section based on the dark matter profiles and various locations. Right? So doesn't that necessarily then push you if you have a large coupling constant? Because it's how much more reasonable with a small coupling constant. You know, microscopic running coupling constants than by the reasons.
Yeah.
Doesn't that push you then toward very large dark matter, particle masses, and especially the lower of the two masses?
Well, it does in a sense. I mean, in a sense, you could have like the most a model that would fit all observation would be like this, like a strongly bound dark matter. Like strongly like a strong force, basically. Because that's basically you're going to form these bound states, and there's no way you can ever excite them. It just looks like cold dark matter from early on. And that's it. Right? This is, but the thing is, we didn't want to go into this direction because it just looks like cold dark matter from early on.
Well, wait a minute. I mean, if I just consider the atomic cross section, it's not negligible.
No.
I have a particle with a GeV, but alpha of say 0.1 or 0.3.
Yeah.
That atomic cross section is probably ruled out, I would think, based on.
But so I showed you these plot, right?
From
the thing is, you have a large enough mass, you dilute, since you have the fixed dark matter density, because it's fixed for observation, if you crank up the mass to 100 GeV or something, then you have very few of these objects around. So even though the cross section is dark, you basically never find each other.
right, but you have to push up the mass.
Yeah. And so that explains the shape of these plots. Right?
Well, the other thing in these plots, you were taking the slightly independent variable from alpha D and MD, which isn't really justified, right? It's just a simple D1.
But the constraint purpose. I'm saying it's just for a given choice of alpha D and MD, we have a bunch of choice of binding energy. We have a certain range that's allowed for a given choice of these two, and that's what this is showing.
Sorry, is MD,
below this, I thought this makes sense.
Is MD the reduced mass, or is
it's
it?
a total mass of mass.
It's a total mass.
The total mass of mass.
So it's like the equivalent of mass. Okay, sorry.
Yeah, that's
Then BD is an independent variable. Sorry.
the thing that determines the number. So maybe I didn't make it.
I guess we should probably stop here and go out for our cookies. And yeah, we will take time to stop for dinner tonight and whoever wants to run.
Yeah, I'll be here for a couple more days.
Yeah, I will. Yeah, I was saying.
Oh, sorry, I
Until
feel
Wednesday.
Right.